Good day, ladies and gentlemen. Welcome to the online masterclass, Optimizing Green Hydrogen Projects using AFRY's Configuration and Optimization tool. My name is Eileen Tang, Assistant Content Analyst at Leader Associates. It's a great pleasure for me to host this masterclass. The class is part of the digital content of our upcoming event, Connecting Green Hydrogen APAC 2023, which will take place on July the 25th and 26th in Melbourne, Australia, serving as a premium platform for industry professionals to gather and exchange knowledge about the latest advancement of green hydrogen. At this masterclass, we are honored to have Dr. Solomos Georgiou, a senior consultant with AFRY Management Consulting, as our keynote speaker. Dr. Solomos will be talking about some of the challenges associated with green hydrogen production and how AFRY's hydrogen optimization tool can help in addressing those challenges in a cost-effective way. Welcome, Dr. Solomos. The stage is yours now.
Thank you, and thank you very much for the introduction, and happy to be here today. Let me start by sharing my screen. So if you could please let me know when that comes up, that would be great. Okay, excellent. Hello everyone, and welcome to the talk today. And thank you for your interest in this topic. We hope you enjoy this masterclass. Before we start, just a quick introduction to myself. My name is Solomos Georgiou, and I'm a senior consultant in AFRY's London office. I'm part of AFRY's hydrogen expertise cluster in management consulting, with experience in hydrogen as well as several electricity markets, especially in Europe and the US. Prior to my time at AFRY, I had the opportunity to conduct research in numerous energy-related topics at Imperial College London. Just a couple of words about AFRY. So AFRY is a global engineering and consulting company with about 19,000 engineers and consultants. We have offices in over 40 countries worldwide. And in terms of hydrogen, we have delivered over 200 projects just since the start of 2021. And that's in over 30 countries. We work right across the value chain, from energy production through to end use, and can provide a one-stop shop for our clients by combining our expertise in consulting and engineering. Now, moving on to today's topic, which is optimizing green hydrogen projects using AFRY's hydrogen project optimization and configuration tool, and why such tools can be very beneficial at the right time in the project life cycle. So in terms of why, well, it comes down to the challenges associated with green hydrogen. And one of the greatest challenges of that has to do with the intermittency of the renewable sources, right? So if we think about the service that a conventional gray hydrogen production system provides, essentially it provides a steady supply or baseload hydrogen service. Now, because we are relying on intermittent renewable as an energy source in green hydrogen production, it is challenging to meet, to provide that service, essentially to meet a predefined hydrogen demand profile in the same way. Now, as a result, flexibility solutions and optimization of renewable energy sourcing, system sizing, and operation of the plant could typically present opportunities to improve the cost competitiveness of such system. Now, in the following slides, we will cover some of the areas that can be beneficial to optimize, as well as some of the challenges associated with them. Now, let's start by focusing on optimizing the renewable energy sourcing strategy and seeing some of the potential benefits in doing that. So if we look at a very simple illustrative example where we use a hybrid system of solar and wind as opposed to using a single source of energy, we can immediately see some benefits which are obvious, such as the decrease in annual and seasonal variability, and that is shown in the first two charts. Now, in terms of hourly variability within the day, in this particular example, there hasn't been much improvement in the variability, but something that maybe is not that obvious immediately is that the benefit in synchronization of supply and demand. And what we mean by that, in this particular example, by introducing wind in addition to solar, we were able to reduce the number of zero generation hours, and that could essentially be beneficial in satisfying certain requirements of the electrolyzer, such as a minimum load factor requirement. Without the need of a flexibility solution such as a battery. Now, obviously, this is very case specific. It can vary a lot depending on the aspects such as location, technologies, weather, and so on. But that is why we need optimization models and sophisticated models to optimize all these aspects. Now, we've looked at the renewable energy sourcing side, but remember that the cost of production is not just the renewable power or the electrolyzer. We obviously have to consider the whole system. And in a cost-optimized system, the optimized combination of the capacities will be determined, as well as the deployment of flexibility solutions. Now, flexibility solutions are in most cases necessary when it comes to green hydrogen production to effectively balance supply and demand and help satisfy some of the requirements of the systems, right? Such as demand or minimum load factors and any other constraints that a system might have. Now, the best selection of flexibility solutions are expected to be project specific, and we use our tool to identify and optimize their deployment. Now, let's go over some of the most important ones we typically optimize for. And we can start by considering any flexibility on the demand side. Now, by introducing flexibility, demand flexibility, we are potentially allowing the supply and demand to synchronize to an extent. But there is obviously limited flexibility in most situations. So although the benefit of having that flexibility in demand can be great, then potential for this can be very limited depending on the constraints associated with the downstream process. And this is something that we take into account and optimize against, both in terms of co-optimizing the production profile of the downstream process, as well as the capacity of the downstream process when that is allowed. And by flexibility of the downstream process, we mean things like, for example, a minimum allowable turndown ratio, a frequency at which the production can change, ramp rates, and so on. But since this flexibility can be quite limited, additional or other flexibility solutions will probably be needed. Now, the next obvious one would be probably hydrogen storage. By adding hydrogen storage, we can potentially fill the gaps, right, between renewable energy resource availability and hydrogen demand or derivative production. Now, storage can essentially fully balance supply and demand when it's provided at sufficient enough capacity. But it can be expensive, and there also can be limitations of how much storage can be added on site. Also, hydrogen storage does not address any requirements from the electrolyzer. For example, like we said earlier, the minimum load factor. For that reason, storage and flexibility in demand might not be sufficient on their own in some systems to balance the system. So what we can, in addition to hydrogen storage and flexibility in demand, we can start thinking about batteries as well to help with balancing of the system. Now, the way that batteries and the whole system operate is something that we optimized to ensure that the optimum capacity is added to achieve security of supply of hydrogen at the lowest cost. And obviously, batteries can help in reducing hydrogen storage requirements, but the most competitive solution would depend on the characteristics of each project, such as the CapEx, the OpEx, the renewable profiles, and so on. Now, again, with batteries, as with the other flexibility solutions, there could be some restrictions on how many batteries we can use, what capacity of battery we can use. They can be expensive. There can be restrictions on how many batteries we can add on site, and so on. So what else can we consider as a flexibility solution? The next obvious one would be, connecting to the grid and the power market. And that would give the system much more flexibility. But again, there can be some restrictions on using the grid. For example, in how much power can be used, the carbon intensity of the grid, power prices, and so on. And once again, this becomes an optimization exercise of how we meet demand at the lowest possible cost while satisfying the conditions of the project. And remember that in most cases, we will need to use projections related to the grid over the lifetime of the asset. That means that we need to have a very good understanding of the power market and how it will evolve over the lifetime of the asset. And if, however, we were able to make use of the grid in the way that we use the renewable power from the solar or wind or any renewable asset, essentially shifting the generation to other periods in the year, obviously that might help a lot. And this is what we typically call temporal correlation, right? So essentially, by doing that, we can reduce the need of flexibility solutions, such as using electricity from the power market or from storage. And that can help the economics of the project. But once again, there could be restrictions on how flexibly we can use the power from the renewables, and that comes down to policies and green certifying criteria that we need to meet to ensure that the hydrogen we produce is green. And we expect that this, in most occasions, will have a big impact on the optimal sizing and operation of the system, obviously. Now, if we go even one step further, we can consider alternative sources of hydrogen as a flexibility solution as well. Now, a lot of existing hydrogen off-takers will have alternative sources of hydrogen supply, right? So, for example, that can be an SMR unit. So co-optimization of sourcing hydrogen from the electrolyzer system and an alternative source could lead to some cost benefits. However, the level at which this can happen can be quite limited, and that can be restricted due to, again, policy, because we will have a blended hydrogen, or due to flexibility constraints in the alternative hydrogen source. Now you can see how this becomes quite complex, and all these flexibility options, considerations, their constraints, in combination with optimizing the renewable energy resource mix and the electrolyzer, do result to a complex problem to solve, and that problem is expected to be case specific, right? So because many of those factors are project specific and site specific. The question is, how do we consider all these aspects in a holistic way to cost optimize the project? Thankfully, there are ways we can address this, and we have developed an optimization tool specifically for this purpose in AFRY. So our hydrogen optimization tool makes this complexity manageable to effectively address such questions, to help our clients understand the options, the challenges, and the solutions relevant to their project. And one of the key features of this tool is its flexibility in the range of systems and configurations it can consider. For example, we could have off-grid systems, completely off-grid. We can have grid-connected systems through PPA agreements and different temporal correlation requirements. We can have grid-connected systems participating in the power market, systems with semi-flexible demand, and many more, as we've covered in the previous slides, the range of flexibility solutions we can consider. We can also test and quantify the impact of aspects such as location, generation and demand profiles, cost and access to the grid, and more. We can capture the risk of weather variability and the uncertainty around that. We can optimize the dispatch of the system to maximize the revenues from the power market, from selling power to the power market, and minimize the cost of buying power from the power market, and many more. Now, in terms of outputs, once again, we have flexibility to tailor the outputs depending on the client's needs and the project. But it's important to note here that we can have annual outputs such as the levelized cost of hydrogen, optimal capacities, cash flow analysis, breakdown of costs and revenue streams, and so on. But we can also go to a much greater detail, looking at hourly dispatch outputs from the optimal simulations, and look at hourly outputs such as hydrogen demand, storage flows and levels, hydrogen production, grid imports and exports, battery power flows, and so on. Now, a typical question we get is where along the lifetime of the project can this kind of optimization be beneficial? The short answer, it can be beneficial along the lifetime of the project, but we see that in order to make use of as much insights as possible, we find that it can be very helpful exercise at the very early phases of the project when conceptual configuration takes place. As mentioned at the start of this presentation, within AFRY, we can help across all of the above phases, and we can work with our engineers in refining the inputs that might arise during the engineering phases. Now, to very quickly explore some of the potential benefits from a conceptual cost optimization exercise using AFRY's optimization software solution, we can look at 3 case studies from a very simple configuration. Here in the list, optimized case study 1, only hydrogen storage is optimized. In case study 2, renewable sourcing, the electrolyzer, and hydrogen storage are optimized. And in case study 3, we optimize all of renewable sourcing strategy, electrolyzer, hydrogen storage, as well as the ammonia capacity and the ammonia production profile within some flexibility constraints. And looking at the results of these illustrative case studies, we can see how much cost benefit there might be in optimizing these systems. In this specific illustrative example, by optimizing the renewable energy sourcing strategy and the electrolyzer, we see that the levelized cost of hydrogen drops to less than half. If we also take it one step further and optimize the off-taker capacity and the production, in this case ammonia, we can see a further drop in the LCOH of 27%. Obviously, this is a very simple example and illustrative, and this can vary a lot on a case-by-case basis. But the key message here is that it is worthwhile occasions exploring if there is any room for optimization. Now, it is also worth stressing that in all of these 3 cases here, we were able to deliver the same amount of ammonia per annum. However, as a result of the optimization and the unconstrained variables we have in the system, the cost of each other differs. And also, we can see that the amount of hydrogen storage needed decreases substantially with the optimization of renewable energy sourcing and the electrolyzer capacity, and even more if we also optimize the ammonia capacity and ammonia production. So to close this, I would like to leave this slide for a few seconds as some summary of what we've just discussed, and open the floor for any questions.
Okay, thank you so much, Dr. Solomos, for presenting us with such an informative and enlightening speech and giving us such a detailed illustration of AFRY's hydrogen configuration and optimization tool. And here I've got some interesting questions based on your speech, and hope that you could further explain and illustrate for me and our audience. So the first question is, since a lot of projects are looking to be connected to the grid, how can the power market challenges be addressed?
So one of the greatest challenges, as a reminder, with using the grid is around being able to use it and still satisfying green labeling criteria, as well as have a good view of how the grid will evolve over the lifetime of the electrolyzer system. And in terms of policy restrictions, we can optimize while limiting access to the grid, and that will give an alternative solution to having a full access. So we can use the policies applied to a specific country or region to essentially optimize accordingly while using the grid and still satisfying those requirements. Now, in terms of the challenge of having a good view of the future, our optimization model is fully compatible with our power market modeling. So one of the core things we do within AFRY Management Consulting is power market modeling and projections, long-term projections. So we can use our very well thought and developed power market level insights and data to best optimize the hydrogen production system. And yeah, does that answer the question?
Yeah, thank you so much. And as we all know, hydrogen storage is a very important part in the whole process. So I'm curious, is there a way to address hydrogen storage restrictions?
Yes, absolutely. That's a very good point. That in some cases, the required storage levels might be more than is actually physically possible or practically possible. So in those situations, we have the ability of limiting how much storage can be added on site and essentially optimizing around that. Right. For example, a system having access to underground salt cavern, potential underground salt cavern storage will have a different, might have a different capacity capability than having overground compressed storage. And depending on the project, we can set those limits and optimize while satisfying those limits. Right? That might mean that more energy will have to be procured. Other flexibility solutions might need to be used as an alternative to additional hydrogen storage. Or it could simply be that additional storage, hydrogen might be able to be purchased from an alternative source during very low renewable generation periods in the year, and we can optimize for that. But all that depends obviously on the project and the characteristics of the project.
Yeah, thank you for your answer. And in your speech, you showed us 3 case studies in order to explore potential benefits from a conceptual cost optimization phase. And I'm wondering, why is there a greater off-taker capacity in case study 3?
Yeah, that's a very good point. So essentially, in case study 3, we need a greater capacity of ammonia production as a result of the flexibility provided. As a reminder, in case study 3, we were optimizing both the off-taker capacity, so the ammonia production capacity, and we had the capability of some flexibility in the ammonia production. So if production is more flexible, it means that it is very likely that greater capacity will be needed in order to meet the same annual production target. But that is still an overall cheaper solution in the example that we showed, even if additional fixed cost of having a larger ammonia plant, if those costs are accounted for. So despite the fact that we might need a bigger ammonia plant, we might still be able to reduce the cost of the overall system.
Okay, thank you for your detailed and professional answers to all these questions. I hope that more and more high-level stakeholders in the hydrogen industry could benefit from applying AFRY's hydrogen configuration and optimization tool. And I can't wait to learn more about AFRY's amazing solutions across the whole value chain in hydrogen industry at our physical event in Melbourne, Australia. Thank you so much for your time today. And finally, I'd like to thank our audience who has watched it here. Hope you find this masterclass useful and insightful and enjoyed it like I do. You could download the presentation slides by submitting your information to review the whole content today, as well as the key takeaways of this masterclass. Please stay tuned to our upcoming digital series as well. See you next time.